Good evening, everyone. Am I audible?
Yes, sir.
So, before we begins today's class, is there any doubt or any questions which you would like me to discuss? TXY equilibrium diagram which NIST data. Is this of any assignments question? Week 6. Is the assignment date of the weeks is over? As in, calculate the isobaric TXY equilibrium data at 101.325 kilopascal for binary system ethyl acetate ethanol and compare the results by NRT and HOC models with the experimental measure data from the NIST database. So what is the doubt are you facing in this problem? Hello? Okay, tomorrow is the last date. If you watch the videos that we have of the problem solving session from of the last week's class, you will be able to answer this question. It is not that difficult. I have solved this type of problems in the previous sessions. I have shown a complete simulation as to how to retrieve the data from NIST and then do regression or perform the binary analysis. Everything I have shown it in previous classes. So refer the videos that have been uploaded in the YouTube from the previous week and try to solve this problem. If still you aren't able to, then the next week we are going to discuss about this. Any further doubts? Okay. So this week, up till now, we have done some basic simulations and we have covered the binary analysis, ternary analysis, and also pure component analysis. We have also learned about how to specify components in the Aspen flow sheet, including the components which are not there in our data bank and how to determine its properties. So from this week onwards, we are going to focus on the on different unit operations in our chemical engineering. For that, we are going to perform simulation on different and specific blocks that are provided by Aspen. So this week we are focusing on the reactors. So the questions that we'll be handling this week will involve the different reactors that are provided in Aspen. So this is the first problem that we are going to simulate on an RCSTR model. So this is the problem statement. So the reaction that we are going to handle is the hydrogenation of aniline. So the problem states that the hydrogenation of aniline produces cyclohexylamine in a CSTR according to the following reaction. We have aniline C6H5NH2 and we are treating it with hydrogen. It is given as cyclohexylamine. The specifications of the reactor are given that the reactor operates at 40 bar and 120 degrees Celsius and its volume is 1200 feet cube, out of which 75% of it is liquid. So since 75% of it is liquid, then the remaining is vapor. For the liquid phase reaction, the inlet streams have the specifications as shown in table 2.1. So this is the inlet feed specification. So in the reactants are aniline and hydrogen. So the reactant pure aniline and pure hydrogen, the temperature at which they're entering is 43 degree and 230 degree Celsius respectively. The pressure of each stream is 41 bar and the flow rate in kilomole per hour is 45 and 160. The fake reaction kinetics data for the Arrhenius law are given as the pre-exponential factor is given as 5 into 10 to the power 5 meter cube per kilomole second. Activation energy is 20,000 BTU per pound mole and the concentration is in molarity. The thermodynamic property that we are going to use is C sub 0, brace property method in the simulation. The reaction is given in first order in aniline and hydrogen. The reaction rate constant is defined with respect to aniline. So we have to simulate the CSTR model and compute the component mole fraction in both the liquid as well as the vapor phase in the product stream. Whenever we are handling problems of this nature, please keep in mind that we have to use all the data that is provided in the problem that is given to us. And to ensure that all the data that are being used in the given problem is that we have to be very much aware of the input sheets that we are handling in Aspen. So for that, try to run this simulation, use this RCSTR model. Once you open the Aspen, first is for the first task is to specify these components that are given in the problem. Second, you have to specify this thermodynamic property. After that, you have to specify the feed streams. That is, these are the conditions that you have to specify. And then you have to specify the RCSTR model. Once you choose the RCSTR model, you are going to get the input sheet where you have to input all the data like the operating temperature and pressure. You have to specify this particular reaction and the manner in which it has been written. Next, you have to specify the volume of the reactor and the fraction of the reactor, that is the 75% of it is in liquid. Then in once you have specified all this, you have to specify the kinetics data where the pre-exponential factor, activation energy and the this concentration term in molarity has to be specified. Once you specify all this, you are going to find that the Aspen has said that the required input is complete and then you have to simulate the problem. So take a few minutes of time, try to simulate this problem on your own. You are going to find this RCSTR model in the model palette of Aspen simulator. So try to do it on your own and then I'm going to show you how to do it from my end. Meanwhile, if there are any other questions, you can ask me. Else, try to take the screenshot of this problem and try to solve it in the Aspen software. Is the question clear? Do you have any doubt in the question that is being given today?
No, sir.
Okay, then try to simulate this problem. Has anybody been able to simulate this problem?
Sir, I am stuck up at that kinetic part. Can you solve it?
Okay. So first we have to specify the components that are defined in the problem. So how many components are given in the problem? We have aniline, hydrogen and cyclohexylamine. So let us first enter this component one by one. So first we have aniline. Next we have hydrogen and last we have cyclohexylamine. Cyclohexylamine. So C6H13 and D1. C6H13. So this is the compound that we have to add. So let us rename these components. So now the components are being defined. We are going to click on next. Next is the method name. Now in the problem we have been specified that we have to use sys of 0 base property method. If this was not given, we could have used method assistant. Since the thermodynamic property is mentioned to us, let us use the stated thermodynamic method. So this is sys of 0 is ideal or Raoult's law. So we have specified the method name. We are going to click on next. Now we are going to run the property analysis setup. If you remember, whenever we used to give any other method names like NRTL or Unifact, we used to get one interaction parameter table. But over here, since it follows an ideal Raoult's law, and ideal Raoult's law means that there are no deviation from the ideal property method, we have not got those interaction parameters for this case. Now, now our properties or the component specification is complete. Next, we are going to the simulation environment. So in the simulation environment, it is being said that we have to perform the simulation in a RCSTR model. So coming to the reactors, over here, CSTR, we are selecting it. Now using the CSTR model, let us try to understand how the CSTR input sheet works. So over here, our CSTR is a continuous stirred tank reactor. It can be used to model one, two, or three-phase reactors. In our case, it is a two-phase reactor. We are having vapor and liquid. So what is the assumption that this model makes? It assumes that perfect mixing is occurring in the reactor. That is, the reactor contents have the same property and composition as their outlet stream. If you recall the basics of chemical reaction engineering, then this is the assumption that we make to model the RCSTR reactors. It is said that RCSTR handles kinetic and equilibrium reactions as well as reactions involving solids, and we can provide the reaction kinetics through the built-in reaction models or through user-defined Fortran subroutine. Since the reaction is being defined to us, we won't be using a user-defined Fortran subroutine. And these are the following forms that we get in the RCSTR model. We are going to look at it in one by one. Okay. So let us start. Uh, so materials, if we hover our mouse over here, you can see the feed. It is the required input and it is saying one or more. Note that in the problem, we have two input streams, that is pure aniline and pure hydrogen are coming as feed. So over here we have to specify two input reactant streams. So this is one stream. Let us relocate this stream to the top, and this is another stream. Let this stream be aniline and this stream is hydrogen.
Sir,
Yes,
sir, can you please repeat the method which we are using this problem, sir?
over here the method is mentioned over here, C sub 0. It is a ideal Raoult's law method.
Okay, sir. Thank you, sir.
So once we have specified the input streams, next we have to specify the product stream. So the product stream is our cyclohexylamine. So this is cyclohex. Let us rename this block as CST. Now once we have connected the streams and specified the input and product stream, our next work is to specify the feed streams. So when we click on next, over here you can see that the aniline stream is being highlighted. So over here we have to specify the temperature first. So pure aniline is entering at a temperature of 43 degrees Celsius, pressure 41 bar, and flow rate of 45 kilomole per hour. So the temperature is 43 degrees Celsius, pressure is 41 bar, and the mole flow is 45 kilomole per hour. If you remember that previously I used to like fill in over here. Instead of filling over here, I am filling it over here to specify that only pure aniline is coming in. Once we specify the mole flow over here, the other mole flow spaces are left blank. then the simulator understands that this stream contains only aniline with the specified mole flow that is mentioned over here. So once we have specified the mole flow of aniline, our next target is to specify the input specifications of the stream hydrogen. So here you can see the hydrogen has been highlighted over here. So hydrogen is coming at a temperature of 230 degrees Celsius and the pressure is 41 bar and the flow rate is 160 kilomole per hour. So here I am specifying it 160. So you can see that blue ticks have come in this stream folders of aniline and hydrogen respectively. Now we are going to click on next. So here you can see that the CSTR setup has come. So over here there are two types of uh, model fidelity or the details of the CSTR can be mentioned. One is the conceptual mode, that is, it is a shortcut mode or the shortcut calculation mode where the heat transfer equipment geometry is not required. However, if we go to this equipment based mode, then rigorous heat transfer calculation using a jacket or coil, that is pot and heat transfer equipment geometry, must be specified. So usually we go for equipment based mode whenever we know that whether the reaction is an exothermic reaction or endothermic reaction. In that case, we need to provide a jacketed CSTR and we need to calculate the heat duty and the coolant flow rate in order to calculate the amount of heat that needs to be removed for the reaction to occur smoothly. Since all those specifications are not mentioned in our current problem, we are going to stick to conceptual mode. So the pressure for operating the CSTR is 40 bar and 120 degree Celsius. So over here you have 40 bar pressure and the temperature that is specified is 120. Now apart from temperature, there are three other options that are given. If you don't want to specify the temperature that is happening, that is the reactor outlet temperature, if you don't want to specify, you can specify the heat duty. Okay, and heat duty is only selected whenever we are using this equipment based mode. Okay, and also vapor fraction. You can see over it here it is written that vapor fraction is not allowed unless vapor fraction option is selected and conceptual mode is selected. So since we are using conceptual mode, we have two options. We can either specify the temperature or vapor fraction. Since the temperature is mentioned in our problem, we are sticking to the temperature of the reactor. Next is valid phases. Over here it is written only vapor only, but we are having vapor liquid, that is two phase. Next is reactor volume. So over here you can see it is mentioned that the reactor volume is 1200 feet cube with 75% liquid, and the option it is given is reactor volume, residence time, reactor volume and phase volume. Okay, so we are going to select this. Now the reactor volume that is given as is 1200 feet cube. So over here let us fill reactor volume 1200 and this is cubic feet. Now the phase is given to us. The phase is condensed phase. We have to select this reactor volume and phase volume fraction. Okay. So the volume we have specified 1200 cubic feet and the phase volume fraction, it is the condensed phase, that is the liquid phase, and it is 0.75, that is 75%. We have specified that. Okay. Now we are going to click on next. you can see that this is the kinetics, or we have to specify the reaction over here. So we are going to click on new. Over here R1 is selected. What is the type of reaction? We are going to select power law. We are going to click on OK. You can see that the reaction R1 is selected over here, but we have not defined this particular reaction R1. So you can still see over here that the required input is still incomplete. If we click next over here, the simulator is going to take us to specify this particular reactant R1. So we are clicking on next. So here you can see that R1 reaction is highlighted. So we are going to click on new. Now the components we have to specify. So what is the component? Remember that the reactants are aniline and hydrogen. And this is the cyclohexylamine, out of which the stoichiometric coefficient of aniline is 1. For hydrogen it is 3, and for cyclohexylamine it is 1. Try to remember this particular reaction. Okay. So first we are going to component is our aniline. Okay. And the second is hydrogen. What is the coefficient? That is the stoichiometric coefficient. Aniline is -1 since it is a reactant, and hydrogen it is -3. This is since its stoichiometric coefficient is 3 over here. Exponent is 1 and 1. Okay, over here it is written for first order aniline and hydrogen. Next is our product. Our product is cyclohexylamine and coefficient is 1. Once we have specified this in our product section, we usually don't have to specify the exponent over here, since we know that the rate of a reaction is always specified with the exponent of the reactants that are taking place in the reaction. Now you can see that the reaction 1 is this one, 1 has been specified. Now we close this. You can see that the reaction that we have in our problem, this reaction has been showing over here. Next we are going to go to the kinetics. Now our reacting phase. Over here it is written for the liquid phase reaction. Okay, so let it be liquid. Note that inside the reactor there will be two phases, but the reaction is taking place in the liquid phase only. Now the value of K. The value of K is given as 5 into 10 to the power 5. So 5 e to the power 5. So this is the value of K that is specified. Okay. Next is our activation energy. Activation energy is given as 20,000. So 20, 1, 2, 3. And the unit is BTU per pound mole. So BTU per pound mole, and the CI basis is molarity. Before entering all this, first let us understand what are these values that are given over here. So we are going to select this over here. So this is the power law kinetic sheet. Okay, in uh, in CRE you must have seen this particular equation where we use this k t by t naught to the power n e to the power minus e by r, 1 by t minus 1 by t naught, and then we have the concentration terms. Okay, so what is r? R is the rate of the reaction, k is the pre-exponential factor, which is usually denoted as uh, for in Arrhenius form we usually denote it as a naught. Okay, then T is the absolute temperature, that is the temperature at which the reaction is taking place. T naught is the reference temperature. If reference temperature is not specified separately, then it is usually taken as 298 Kelvin. N is the temperature exponent, that is to the power n over here. Now, for this same equation to be converted into Arrhenius equation, this n value it becomes 0. Then the Arrhenius equation we get k e to the power minus e by r 1 by t minus 1 by t naught, and then the concentration terms. E is our activation energy. This is specific to the reaction. R is our gas law constant. This is the product operator. Over here, you can very well understand from the equation it is going to be C of aniline into C of hydrogen, and this alpha is the exponent of the ith component. So if you remember that the exponent that we had filled was 1, because it is written over here that the reaction is first order in aniline and hydrogen. So that is why we had specified 1 over here in the reaction input sheet that we have specified just before opening this sheet. Ci is the concentration of the ith component and alpha is the exponent of the ith component. So this is what all these notations mean inside this particular power law kinetic factor formula. So someone was having difficulty in this. Is the doubt cleared?
Yes, sir, now clear.
So once we have specified all these values, it is telling that the required input is complete. Now if we're going to click on next, it is going to ask whether we want to run the simulation. We are going to click on OK. So here the result is obtained. If we look at the pressure, temperature and vapor fraction, then you can see that aniline, it is pure liquid, the vapor fraction is 0. Hydrogen is coming in a vapor phase, that is 1. And this is a mixed stream where 0.3% of it is in vapor, when the remaining is in our liquid form. So approximately this is 0.37 is vapor. So what is the remaining? Uh, Liquid is in around 0.63. Yes. So 63% of it is in liquid and 0.37 or 37% of this stream is in vapor form. So what was being asked from us? It was asked like we have to compute the component mole fractions in both the liquid as well as the vapor product. So for that we have to come to our result summary. Over here we have streams. Next is our cyclohex. So this is our product stream. So coming down, here is the vapor phase mole fraction. So let us take a screenshot of this. Next is our liquid phase mole fraction. Is the problem understood? Is there anyone who have any doubt regarding this problem?
No, sir, clear.
So let us do another problem. So over here, previously we had done RCSTR. Now we are going to do R plug, that is plug flow reactor. So this is the problem statement. The combination of two benzene molecules from one molecule of diphenyl and one of hydrogen. The elementary reversible Weber phase reaction occurs in a plug flow reactor, that is benzene. This is a reversible reaction, diphenyl and hydrogen. The forward and reverse reaction rate constants are defined with respect to benzene. The vaporized benzene with a flow rate of 0.02 pound mole per hour enters the reactor at 1250 degree Fahrenheit and 15 psi. The data for the Arrhenius law are given below. So this is the data for the Arrhenius law. Over here you can see forward reaction and reverse reaction. Since a reversible reaction is taking place, so we are going to have one forward reaction and one backward reaction. Okay. Now the CI basis, previously it was in molarity basis, but this is over here is in partial pressure. The reactor length is 36 inch and the diameter is 0.6 inch. It operates at inlet temperature. Same property method we have to use, C sub 0 thermodynamic model. So our first objective is to compute the component mole fraction in the product stream, and our second objective is to produce a plot of reactor molar fraction, that is mole fraction versus the reactor length, as to how the reactor molar fraction or the reactant mole fraction is changing. Let's say if we select benzene, how the concentration of benzene is changing across the reactor length. This first part A is can be done. So try to solve this problem. Now comparing to the previous problem that we have done over here, it is a reversible reaction. So no need to get worried about. It is the same procedure that you have to follow. Just remember that since reversible reaction is taking place, previously we had defined only one single reaction. In this case, you have to define two reactions. That is one forward reaction where benzene is changing to diphenyl and hydrogen, and then where benzene will be treated as the reactant and diphenyl and hydrogen as the product. In the second reaction, that is the reverse reaction, you have to treat diphenyl and hydrogen as the reactant and benzene as the product. And over here you can see that the forward and backward reaction data for the rate constant and the activation energy, everything is given. So try to solve this problem. Take few minutes of time. We are going to discuss this problem later. If you are having any doubts, you can ask me in between for simulating this problem. Has anyone been able to do this?
Yes, sir, doing it.
Sir, in reactor type, which type we have to choose, sir?
You have to use arc plug reactor. It is there in the model palette. Do you want some more time or should I start solving it from my end?
Sir, 2 minutes more.
Sir, in
Okay.
specification option, sir. Specification option. Reactor
Okay. Okay.
specification.
Reactors.
Sir,
You are able to find out the reactor model that is specified, right?
Yes, sir. R plug flow reactor I have selected, but reactor type in specification that one.
sir, earlier we have selected power law equation similar to here with reacting
Yes.
unit.
Yes. This also you have to use power law only.
Sir,
Yes.
sir, face of the products, what we have to given, sir?
Phase of the product. You don't need
Yes,
to
sir.
specify the phase of the product. The product phase will be selected, will be determined based on the input specifications that you are giving.
Yes, sir.
So over here, is it asking that phase of the product?
Yes, sir. Stream, sir.
In streams,
Diphenyl hydrogen, sir.
diphenyl.
Yes, sir.
You are specifying benzene, right, as the input stream.
Yes, sir. But it has the product streams, face of the product stream, sir.
Then keep it as vapor liquid because you are getting diphenyl and hydrogen both.
Okay, sir.
Done, sir. Uh, A part is done. B part, I don't know how to do it.
Okay. Try to see the options that you are getting over there. Check the different, like on the left hand side, there are multiple options right over here in the simulation tab. Try to find out any suitable option from which you can derive this plot. Meanwhile,
Uh,
let
okay,
me
sir.
do this simulation. So over here, you can see that there are three components that we need to specify: benzene, diphenyl, and hydrogen. So let us first specify benzene. Next is diphenyl. Diphenyl, and last is hydrogen. Now the components are specified. We are going to click on next. The method name, we are going to use sysop0. We are going to click on next. We are going to run the property analysis. Now we are going to come to simulation. In reactors, we are going to select R plug reactor. So this is the plug reactor. We are going to enlarge this, rename this as R plug. Now material, we have feed, and we have product. So this is feed and this is product. Now in feed we have pure benzene. Okay. So if we click on next, you can see over here that the feed stream is highlighted. So what is being said that the flow rate is 0.02 pound mole per hour and enters the reactor at 1250 degree Fahrenheit at 15 psi pressure. So this is 1250 Fahrenheit and the pressure is 15 psi. And the mole flow, it is 0.02 pound mole per hour. 0.02 and the unit is pound mole per hour. Okay. Now we are clicking on next. So here we are in the R plug reactor. Someone had asked the phase of the reaction. In the problem, it is given that it is a vapor phase reaction. Okay. So what are the reactor types that we have? Reactor with specified temperature, adiabatic reactor with constant thermal fluid temperature, concurrent thermal fluid, countercurrent thermal fluid, specified external heat flux profile. So what do we have over here? What type of reactor did you choose for doing the simulation?
RPFR.
No, that is fine. In this particular sheet, what did you choose?
First option.
With specified temperature.
Yes, because it is carrying out at a feed temperature only. It is mentioned in question.
Yes, correct. So this is the specification that we have to use, reactor with specified temperature, and since the process is taking place at the feed temperature only, so we are selecting it as constant at inlet temperature. If we have different temperature of operation, we can specify this. We can also specify the temperature profile, because with progressing reaction, sometimes the temperature of the reaction changes. So in that case, across the PFR, the temperature profile will also be generated. So in that case, we can give the temperature profile. Over here, we have to write down the length of the reactor, that is at particular length, what is the temperature we want to achieve. Like that, we can model this reactor. Next is our configuration. So over here, we have only single reactor. Over here, if we selected multi-tube reactor, then in case we have to specify the number of tubes, and it is said that the diameter varies along the length of the reactor, then in our case it is not happening. So we are going to select only this reactor dimensions. Now the length and diameter of the reactor is given to us. The reactor length is 36 inch and the diameter is 0.6 inch over here. So what is the reactor length? 36 inch. 36, this is inch, and the diameter is 0.6 inch. Now going to next, we have to specify the reactions. The reaction type is going to be power law. We are going to select OK. So next we have to specify the reactions that are taking place. Now we are clicking on new. So the first component is benzene. First we are specifying the forward reaction. The coefficient is -2 because the stoichiometric coefficient over here is 2, and the exponent we are keeping it as 1. In component over here, this is diphenyl. Coefficient is 1, and hydrogen. This is also coefficient 1. Now you can see the forward reaction is mentioned. Now we have to specify the backward reaction. So the component is diphenyl, coefficient is -1, exponent is 1, and hydrogen. Coefficient is -1, exponent is 1. And the component that we're going to get is benzene. The coefficient is 2. So you can see that the forward and the backward reaction both are mentioned. Now we are going to come to kinetics. So the first is 1 is the for the forward reaction. Okay. And remember that the reacting phase over here, it is saying that the reversible vapor phase reaction is taking place. So over here we have to select vapor. Okay. Next, what we have to do, we have to fill up these forms. That is the forward reaction K is 3.2 into 10 to the power minus 6. So this is 3.2 e to the power minus 6. And the activation energy is 3200 calorie per mole. 3200 calorie per mole. Now the concentration basis, it is given, it is in partial pressure. If I am not wrong, it is vapor phase, it has to be, yes, CI basis is partial pressure. So over here we have to select partial pressure. Now For the first reaction, it is specified. Similarly, for the second reaction, the reacting phase vapor, the K value, it is going to be 1 into 10 to the power minus 5. For activation energy is 3200 calorie per mole. And the CI basis, it has to be in partial pressure. Now you can see that the required input is complete. Now if we click on next and if we run the simulation, so the results are available. So the first part is the compute the component mole fraction in the product stream. So coming to the streams, this is our product stream, and you can see that the molar vapor fraction is 1, that is the entire reaction has taken place in the vapor phase, and this is the mole fraction of the vapor phase.
Hello, sir.
Yes.
Sir, I got benzene 1 and diphenyl 0 and hydrogen 0. Matlab, not in this fraction.
So it is approximately the same value only. It might be because of that version difference you are getting different answers.
Okay, sir.
Now what we have to do is we have to find out the variation. So over here you can see that there is this profile plot over here. If you come to the profile plot, you can see over here that with variation of length, from this plot wizard over here, we have to select the composition. So over here you have the reactor molar composition. Next we are going to select benzene and then click on OK. So here you can see that there is very negligible change because the consumption of benzene, the initial was molar fraction was 1, and over here this is almost constant. Let us just look at this part once again. So this is how you can plot the variation of the composition of the reactant with respect to the length of the reactor. The consumption of benzene is very less, so that is why there is not much variation that you can see inside the graph. If there was consumption of benzene, then you would have seen a variation in the graph over here. Is there any doubt?
No, sir.
There is one problem that we have mistake that we have done. Can you tell me what is the mistake? That is why there is hardly any change over here. I had told you about, actually the mistake is from my end only. I had said the coefficient should be a stoichiometric coefficient, but no, it should be -1 for reactance, and for coefficient exponent it should be the stoichiometric coefficient that we have, that is given in the problem. So this 2, it should be treated as the exponent, because if you remember, when we specify the rate of the reaction, we take the stoichiometric coefficient to the power of the, in the power law we take this stoichiometric coefficient as the power in the concentration term. So in the previous problem also, if you have done it, so make that change. So that is one mistake that we have performed in the previous problem as well. But since there was variation in the product profiles, I did not see that properly. Over here, you don't have to give the exponent in the product terms, but over here you can see this coefficient is -1. Since this is the reactant, this is going to get consumed. So we are going to give this as -1, and the exponent is 2, which is the stoichiometric coefficient of the reactant. Similarly, we have to change this as well. This is getting consumed. This coefficient is 1. And first is this one is 12. I'll check this problem once again. In the last part, what I have done is actually inside over here in the problem, it was said that the reaction rate is with respect to benzene. So what I did was I have just divided this entire equation by this value, that is by 2, and then I have made this unit, then I have made this coefficient 1, and then I have rewritten the rate of reaction. However, it is not reflecting any change in the product streams. I need to check why this is happening. But this is how you can do this simulation. I'll take up this problem in the next week as well as to why there is no change in the uh, reactant. I'll see it and I'll let you know. Let us do the other problems today. I'll get back to you.
Sir, excuse me, one
Yes.
doubt.
Uh,
Sir, in the reactor first page, setup page, we have given specification. Next is configuration. In the configuration, I have given vapor. Then it is going to streams. In the streams, it is showing diphenyl and hydrogen. Where when I am entering vapor, the system is not taking. Matter is coming.
you have selected
So
vapor only, right? This part over here. You can see my screen.
yeah, I can see you. Yeah, vapor only first I selected.
Uh,
Then after that, streams is coming. In that, diphenyl and hydrogen is coming. This page, correct. This page it is showing diphenyl and then second one is hydrogen.
is your process flow sheet specified like this?
Uh, no, sir. Two components I have given in the product.
No, you give one component only. Two components are not there. It is going to be a mixed stream of both the products.
Okay, okay,
If you do that, then that problem won't be there.
okay, okay,
Okay.
okay, okay, okay.
Let us try to debug this problem once as to why this variation is not coming. Just give me a few minutes. Let me just check it once. Like, what is the problem that we have made? Because I'm not finding anything that I haven't mentioned in the question. Let me just check it once.
Sir, what is the correct answer for that question?
So, which correct answer? For
Uh,
which question?
as per the textbook for this question only.
For textbook. Actually, this is an unsolved problem. I'm trying to solve it.
Okay, sir.
Just because the reactant should have some variation, right? It is getting consumed.
Right.
We are finding no change in the profile, so that is why I'm stuck, as in why it is not happening.
Okay. Hello, sir.
Yes.
Sir, even if I keep only first reaction,
Hmm.
I am getting 100% benzene in the product.
Yes, that is the problem that we are facing, right?
Um,
Is the
I did not.
question.
I did not add the reversible reaction. Only
Hmm.
first reaction. E- Even in the absence of reversible reaction, I am getting 100% benzene.
Yes, I can understand. It is that problem. Either the question that is given is wrong, that is the data that is given is wrong. I think the data that is given is wrong only because everything we have specified according to the problem that is given to us. This shouldn't be happening. If I am doing it like this, then it is telling that it is not in mass balance. There will be mass balance, mass imbalance because two products are coming over here.
Sir, can we check the amount of activation energy we are getting from the conditions specified in the problem?
For that,
Can-
we need to perform experiments. We
Okay.
cannot check it like there is no
Is it
mathematical.
not available in the system?
No, it's usually not. No, it is not given by Aspen. There might be some error in the problem that is given to us.
Hello, sir.
Yes.
When Professor Pravir Kumar he was teaching about this PFR reactor,
Yes.
he was not putting exponent value in product side. He was putting 0 0.
Yes, by default, these values are zero only. If you don't put anything, the default value that is given is zero. That is, we usually don't put any exponent on the product side. We only need to specify the exponent in the reactor side only.
Yes, and uh, it is written that it is a uh, just a minute. Mm, elementary reversible reaction, right? So if it is elementary reaction, then according to benzene it is second order reaction, and when we see in reversible, then according to diphenyl and hydrogen it is first order reaction,
Yes,
right?
yes. That is where I'm thinking like how do we write the reaction so that we get the results. There is one way we can do like the thing that I was trying. Like if I divide this entire reaction by two, then what happens is this the coefficients become zero point 0.5 over here. That is what I'm trying.
Yes, I got that. But even if we divide and do that all mathematics thing, order of reaction remains constant, right?
Yes, yes. So the order of the reaction is second order reaction with respect to benzene. Even with respect to the reversible reaction, this also order will be 2 because the coefficient over here is 1 and 1.
Yes, right.
So the order is going to be 2. That is not an issue over here. That is only what I'm seeing. Like what is the error that why aren't we getting any variation in the product stream? Okay, let I'll like try it some other time and I'm going to get back to you. Like you also tried from your end and see if you are able to find out the error that is happening. Either that or this entire question is somewhat long that is given. We'll see it in the next class.
Okay, sir, we will try in fresh new simulation.
So this is also an art plug model. Over here, we are going to use a different kinetics. So up till now, we were using this power law. Now we are going to use LHHW kinetics. Now LHHW kinetics is usually used for adsorption problems. So here, these kinetics are useful in catalytic processes. So over here it is said that acetic anhydride manufacturing, the cracking of acetone produces ketene and methane according to the following irreversible vapor phase reaction. So the phase of the reaction is given to us vapor phase. So acetone, it changes to ketene and methane. The reaction is first order with respect to acetone. Pure acetone feed with a flow rate of 130 kmol per hour enters a PFR at 725 degrees Celsius and 1.5 atmosphere. The kinetic data for the Aspen plus simulation are given below. So this is the kinetic data for the Aspen plus simulation. The unit of the pre-exponential factor clearly indicates the CI basis. To use the Langmuir, Hinshelwood, Haugen and Watson, that is the full form of LHHW kinetic model, set 0 for all the coefficients under term 1 and for all coefficients except A under term 2. Take a very large negative value for the coefficient A. The sample adiabatic PFR is 3 meter in length and 0.6 meter in diameter. We have to use the CSOP 0 base method and compute the component mole fraction in the product stream. So let us try this problem. So we have acetone. We have ketene and we have methane. The property method is CSOP 0. Next, we have to specify the reactors. We are going to choose R plug. So over here we have one acetone, one that is one reactant stream acetone, and one product stream. So this. So first we have to specify the acetone. Pure acetone with a feed flow rate of 130 kmol per hour enters PFR at 725 degrees Celsius and 1.5 atm. So 725 degrees Celsius and 1.5 atm. Next is the flow rate of 130 kilomole per hour. Acetone is 130 kilomole per hour. Okay. Now we are going to click on next. Now the reactor is, we are going to react it with the specified temperature. It is constant at the inlet temperature. Now coming to the configuration, it is given that the PFR is 3 meter in length and 0.6 meter in diameter. So this is 0.3 meter in length and 0.6 meter in diameter. Now reactions, we are going to select R1, and what will be the reaction type? LHHW. Previously we used to select power law, now we are going to select LHHW reaction. Okay. Now we have to specify the reaction. Now coming to the input, so this is an LHHW kinetic sheet. We are going to have different parameters that we need to fill. So this is what the LHHW rate expression looks like, where R is the rate of the reaction. If you remember, then I had said that LHHW kinetics is usually used when there is adsorption taking place or in catalytic reactions. So over there, different driving forces come into action. So this R, this reaction rate is determined by these three factors over here. One is the kinetic factor, next is the driving force expression, and in the denominator it is the adsorption term. So the kinetic factor is the this factor that we already know from the power law that we have taken. It is a generalized power law equation. Next is the driving force expression. So what is the driving force expression? It is the competitive nature of the reactants that are taking place in the reaction, where Ci and Cj are the concentration of the reactants I and J. That is the different reactants that are present in our system, and K1 and K2. So what is K1 and K2? It is the pre-exponential factor of those reactants. Okay. Then we have the adsorption term, which is denoted by this. If you go to this sheet, you are going to see all the different terms and the different parameters that we have to specify for specifying this particular LHHW kinetics. So first let us specify the reaction. So what will be the reactant? Can anyone tell me? We have acetone over here.
Acetone.
What will be the coefficient? Huh?
All are 1. -1.
This will be
Fine.
-1.
Yes.
Then this is ketene and methane.
Ketene and methane.
Now we are coming to the kinetic part. Now if you see that this kinetic is a bit different from the ones which we have done previously. So first we have to specify the reacting phase. The reacting phase is going to be vapor. Okay. Next we have to specify these terms. So what is the value of K? 1.1. This is 1.1. Then we have to specify the activation energy, which is 28.5 into 10 to the power 7. So 28.5 e to the power 7. Okay. And T naught is given to us, the value of N is 0, and T naught is given to us 980 Kelvin. Now, if you see that we have to specify the driving force as well, because it is written over here. Like we have to take a very large negative value for coefficient A. So now what we are going to do is we are going to select the driving force option over here. Once we open the driving force option, we are going to find the reacting phase, which we have specified as vapor. The CI basis is molarity, and then we are going to find the terms of enter term 1. So how we are going to fill it is the exponent.
Sir, what is term?
Huh?
Enter term, that part means what does that mean, term?
These are the coefficients of the driving force. If you see over here, it is written, it lets you type the coefficient A in the first driving force term. Okay, you need to see this. So this is the driving force. Okay, we are specifying this particular part on the Aspen. So in LHHW kinetics, you need to remember that these are all, when these kinetics they reach an equilibrium, when the driving force it tends to 0, right? So in this driving force expression, this is the adsorption expression dialog box over here. So we need to specify these components A, B, C, and D to get the values of this constant K. These over here, we are solving this particular equation for which these coefficients value has to be given. Like K1 is equals to constant, coefficients for A, B, C, D for driving term, constants for term 1. Like how many driving force we are going to have? Since we have only one component over here, we are going to have only one driving force. If there were more than one, then this second term would have come. Now to specify over here, this is the driving term constants for term 1, that is for acetone. We need to specify this A, B, C, and D value. Did you understand?
Yes, I understand that part, that we have to put a very big negative value for A to specify this K1, right?
Hmm.
Yeah, I got that.
So here it is telling under term 1 and for all coefficients except A under term 2. So coming to driving force, the exponent over here, this is 1, this is 0, and this is 0. Concentration exponents for reactants. For term 1, all of these values are 0. And for turn 2, this is 0. For this, we need to specify a large negative value. So let me set these value as 1 e to the power minus 10. Now we have set the driving force. Now we are going to click on next and we are going to run the simulation.
Sir, why you put that exponent 0 for acetone in term 2?
Because in the this part over here we are not considering acetone, right, in term 2. That is why I have put it as 0.
Okay.
Joule per kilomole. Huh. So over here this unit was creating the problem. So this is the results that we have got. So what is being asked from us? We have to compute the mole fraction in the product stream. So the product stream mole fractions. So this is the mole fraction of the product stream. This is the mass fraction. So now for this, if we look at the profile, we're going to get a proper plot. Go to the composition profile and we select all. So here you can see that how this acetone is getting consumed across the length of the reactor, while the ketene and methane, they are actually uh, on top of one another, this graph, and this is getting increased. So this is how we should be getting the graph of the previous problem as well, where the reactant will be getting consumed and the products will be formed. So I'll check that problem and I'll discuss it in the next class. So if there is doubt, you can ask me, or else I can end the class now. Hello.
Hello.
Yes.
Sir, can you explain the reaction kinetics once again for this problem, recent problem?
So this is the LHHW kinetics. Now the rate of the reaction is determined by various forces that come into action when the reaction is taking place. So over here we have a kinetic factor, a driving force, and the adsorption term.
So screen is not shared.
So, so there is the kinetic factor and the driving force and the adsorption term. Now what is the this kinetic factor? We have already seen it previously. Now this becomes our the driving force expression. So what is the driving force expression? Usually LHHW kinetics is coming comes into is considered whenever we handle catalytic reactions. So in catalytic reactions, if there are more than one components that we are handling, then there is a competition as to which component is going to get adsorbed onto the surface of the catalyst. So over there, we have this differential term where I is equal to 1 to n Ci to the power alpha I minus K2, J is equal to 1 to n Cj to the power beta I, where K is the pre-exponential factor of those associated terms and C is the concentration. Okay. Now, depending on this driving force, if you remember, I had selected acetone on one because over there only for these are the different terms for the driving force. Okay. So we had only one term, that is acetone, that is going to get absorbed because that was the only single reactant that is being taking part in this reaction, and the rest I had set it as 0. So For uh, for this K1 over here, when acetone only one reactant is there, only this single term comes into the picture. So this becomes our driving force expression. And next is our adsorption term. Now adsorption term, we have this equilibrium constant Ki followed by the concentration of the terms that are taking place in the reactants. So over, and what is Cj? Cj are the products and I is the reactant. So over here, if you see, there are, I have defined that this is the rate of the reaction, K is the pre-exponential factor, and this unit I and J, they are the indices. That is, if you have three components over here, then I, J, and K, they become the indices of the three components that are taking place inside the reaction and inside this rate equation. What else do you want to know? Tell me. Hello.
Sir, when we put those values in Aspen term 1, term 2,
Hmm.
um, I did not get the whole of that idea.
So over here, if you see this, these are constant values. Okay, the coefficients A, B, C, and D for the driving term constants. So when you are trying to evaluate this particular term over here,
Okay.
okay, so for that, what you need is you need to turn one. That is our acetone. I have
Okay.
kept one over here. Next, what we are doing is we are filling up. We are filling up these coefficient values. Now, in the problem, it is given that this is the predominant reactant or the only single reactant that is taking place in this catalytic reaction, right? So for that, the driving force, it has to be maximum. So we have set the acetone value as coefficient as 1 over here. That is the concentration power. That is this term. This alpha I coefficient, we have set it as 1. Next, if you hover over here, it it is telling that it lets you type the coefficient in the first driving force term. That is the first term, that is K1, and the product of Ci alpha I. So how it is being calculated? This is calculated based on these correlations. Why isn't not sure? Based on this calculation, which is ln constant 1, that is ln K1 is equals to A plus B by T plus C into ln of T into D of T. This is how that is being calculated. We are just setting those values to calculate the first term of our driving force. Since term 2 is not there, we are setting this A value as negative. Why we are setting this as 0 as a very high value? So that the second term effect in the reaction rate constant is negligible. That is why.
Okay, sir.
Are there any more doubts?
No, sir.
Thank you then. I'm ending the class now.